Major requirements for life: staying alive. Your body needs a lot of different nutrients and gas level and pH level. In fact, if you look at these different things that the body needs, the cell needs to stay alive, you have blood gases, oxygen. You have to have a way of getting rid of carbon dioxide. You need nutrients, glucose, amino acids, fats, nucleic acids, electrolytes, sodium, potassium, calcium, fluids such as water. You need to maintain your body at the right temperature, maintain those cells at the right temperature. You need to have a way of getting rid of waste. You want to maintain your body's pH between 7.35 and 7.45. Actually, that's your blood pH between those levels. You have to have a way of circulating all of these substances that the body needs and getting rid of waste. Well, we call these different things that the body needs, we call those variables because their value can change over time. Homeostasis is all about keeping those different variables in check at the right level. It's a condition of dynamic consistency, which means it's the organism's ability to maintain a relatively stable internal environment despite changes inside and outside that body. Homeo means stays the same, or unchanging. Stasis means constant. You look at these two terms and they seem contradictory. Dynamic, moving, changing; consistency, staying the same. The reason why they use this term is that you want to keep the body at a relatively stable, constant state, but there's going to be variation in that, slight variation. That's a dynamic. So, for example, you have a set point where you want to keep, for example, normal body temperature at 37 degrees Celsius. Well, your body's going to heat up and it's going to cool down. It's going to heat up and it's going to cool down. But you don't want to get too far away from that set point. And so the dynamic is that you have variations all the time, but your body works to keep those variations relatively limited around this set point. So, homeostasis. The function is to maintain all physiological values within certain limits or at their set point that we were talking about. For example, you keep the body temperature at 98.6 degrees Fahrenheit or 37 degrees Celsius and maintains adequate nutrient oxygen levels for cells to flourish. Now, homeostatic variables are not kept rigidly fixed upon a single value. They are kept within a certain range. So when you look at this, body temperature, is it always exactly 98.6 degrees Fahrenheit? And people will have variations in that. It could also be normal. You could have a normal body temperature of 99 degrees Fahrenheit or a normal body temperature of 98.3 degrees Fahrenheit. With this example, this is a relatively normal one that most people have. And it's not always right at 98.6 degrees Fahrenheit. You have variation in that. Now, when you control your body temperature, there's an area in the brain called the hypothalamus. And the hypothalamus is a thermoregulatory center within the body. And it's going to measure temperatures, well, within the blood. And it also has receptors for temperature sensors in the skin and other areas of the body that will send signals into the hypothalamus. And the hypothalamus is going to elicit responses from effectors to either increase the temperature or decrease the temperature of the body. So, for example, if you have a homeostasis, you have normal body temperature, and that normal body temperature is disturbed, meaning that you have a rise in body temperature. You'll have receptors that are going to detect that, and those receptors are going to send signals to the control center of the hypothalamus. The hypothalamus is then going to, it's the control center, and it will decide how to handle this change in temperature. In this case, with a rise of temperature, the hypothalamus is going to send signals to effectors. These effectors, such as sweat glands in the skin, are going to increase their secretion. You're going to have more sweat. Blood vessels at the skin are going to dilate to allow more blood to get to the surface to release heat. And that increased heat loss due to the evaporation of the sweat and through the dilation of those blood vessels to get more heat radiating from the body is going to bring that temperature back to normal. So you have a increase in temperature, and then through the effect of the effectors of sweat glands and dilation of blood vessels, it's going to decrease that temperature. And if it gets too low, the hypothalamus is going to send signals that are going to help to increase the temperature again. So you always have this rise and fall around a set point. And you probably experienced this when you've been ill. What causes a fever and chills? Well, you have in your lymphatic system, part of your lymphatic system, you have these macrophages, these white blood cells. And if you get a wound, let's say in the body, and you get bacteria that can come through that wound, or you get exposed to bacteria from an illness, or somebody else who's ill, or things that are in the air, these macrophages will take that bacteria, it'll gobble them up by phagocytosis, and then as that bacteria is degraded, that macrophage will release substances called pyrogens. Pyro means fire, and gen is to generate. So these pyrogens, one of which is called interleukin-1, gets released by the macrophage. It goes through the bloodstream, goes up to that hypothalamus here. Remember, that's your regulatory center of the body. And then that hypothalamus, in response to these pyrogens, in this case interleukin-1, is going to produce substances called prostaglandins. Now, prostaglandins induce the hypothalamus to reset the body's thermostat, and it's going to set it at a higher temperature. So instead of being at 98.6 degrees Fahrenheit, the hypothalamus raises its set point to 103 degrees Fahrenheit. Once it does this, then it has to send signals out to the effectors to raise your body temperature. So your muscles are going to start shivering. You're going to have vasoconstriction of blood vessels at the surface of your skin. But the temperature is going to increase slowly, and that's where you get those that fever, that chills, because your body's increasing in temperature until it hits that new set point, 103 degrees Fahrenheit, and you say you have a fever. Well, once the bacterium, once the illness is under control and you are killing those things that are causing those pyrogens to be produced, then without those pyrogens, you don't produce the prostaglandins. The hypothalamus resets its temperature back to normal. Body is heated up to 103 degrees Fahrenheit, and you have to come back down to normal. Well, in order to do this, you have to release heat. So you start sweating, and it's a way to evaporate that heat off, and that lowers your body temperature. And that's where you get the all the symptoms of, well, when the fever breaks, they say, to cool off your body. Your body gets out of homeostasis, then that's when disease can happen. Now, regulation of homeostasis is maintained by feedback systems. We'd already talked about how you have a control center, you have a receptor and effector. Well, this feedback system helps to cycle the events which a condition is continually monitored, evaluated, and changed if necessary, and then monitored, reevaluated, and so on via this feedback system. So you have three components of a feedback system. You have a receptor, a control center, and an effector. So feedback systems. What is the receptor? The receptor is a sensor that monitors and detects changes, which is called a stimuli in a condition. And those different conditions are called variables. So basically, you have a sensor that sends information to a control center via nerve impulse or chemical signal. So what the control center does is it sets the range of values at which the condition should be maintained and determines an appropriate response based on the information it receives from the receptor. Now, its output via nerve impulse or chemical signal is going to affect effectors. So what are the effectors? A cell or organ that receives output from the control center and produces a response that changes a condition by either depressing negative feedback mechanism or enhancing positive feedback mechanism, that original stimulus. And we're going to look at different examples such as skeletal muscles or effectors. They cause you to shiver in response to cold conditions. And that cold conditions was a stimuli. Now, when you classify these feedback systems, they can be classified as either positive feedback systems or negative feedback systems. And we look at negative feedback system. The main thing here is that in negative feedback systems, they reverse the direction of the initial change in the condition. So, for example, if you have a rise in blood pressure, your body's going to work at changing that rise in blood pressure to bring it back down to normal. It's going to decrease. It's going to go in the reverse direction. Blood glucose level. If you have a rise in blood glucose level, then we're going to see by negative feedback systems, your body's going to work to decrease that blood glucose level. So it decreases the original stimulus. Now, to give you an example here, let's say you have homeostasis where your blood sugar level remains at about 90 milligrams per deciliter, 90 milligrams per 100 milliliters. And you have a rise in blood glucose level. You eat a piece of candy, you eat a candy bar, and your blood glucose level begins to rise above that set amount right here. Well, the high blood glucose level is going to be detected by insulin-secreting cells of the pancreas. And these insulin-secreting cells are going to make insulin. And that insulin travels through your blood, and it helps that glucose get into your body cells and into the liver. And by getting that glucose into the body cells and liver via insulin, it's going to decrease your blood glucose level. So your blood glucose level comes back down to normal. A negative feedback mechanism. You had a rise in blood glucose, then your body had this feedback system which ultimately lowered blood glucose level. It went in the reverse direction. So it's negative feedback. What if you have a decrease in blood glucose level? You haven't eaten in a while and your blood sugar level is getting low. Low blood glucose level is detected by glucagon releasing cells of the pancreas. These cells are going to release glucagon, and glucagon is going to go through the bloodstream. It's going to go to the liver, and the liver has storage forms of glucose known as glycogen. And it's going to stimulate that liver. That glucagon hormone will stimulate the liver to release glucose into the bloodstream. And that glucose in the bloodstream is going to raise that blood glucose back up to normal. So your original stimulus was a decrease in blood glucose level. The body's response, produce glucagon, break down glycogen supplies in the liver, get that glucose into the blood, and raise it back up to normal. So it's called a negative feedback system. Original stimulus, decrease in blood glucose level, response to the body, increases it back to normal. Negative feedback mechanism. When does the negative feedback process end? The process ends when that condition, that variable, is back within its normal range. Negative feedback process begins when a particular variable leaves a homeostatic range, and then that negative feedback process is self-terminating. When it comes back in a normal range, it shuts down. For example, when you go from a lying to a standing position, you're lying down, your blood pressure is lower. You stand up, that blood pressure falls because you have blood tending by gravity to pull lower in the body, so your blood pressure falls. Well, you have receptors in the aorta. These receptors are called baroreceptors in the aorta, and you have baroreceptors in the carotid arteries up and through here, and they're pressure receptors. They detect a decrease in or increase in pressure, and then they send those signals into the medulla oblongata of the brain, which is a control center for blood pressure within the brain. So when you have a blood pressure falling, these blood pressure receptors, baroreceptors, they send signals to the medulla oblongata, which is your integrating center or your control center. The medulla oblongata goes, oh, we have a decrease in blood pressure, so let's elicit responses to increase blood pressure. It sends a signal to the heart to increase heart rate, increase force of contraction. It's also going to send signals to vasoconstrict blood vessels, and both of those are going to cause a rise in blood pressure, which is going to bring the blood pressure back to normal. So it's negative feedback. Original stimulus, a decrease in blood pressure. Response to the body, increases blood pressure back to normal.